So if I fall into one of these black holes, can I travel across the universe?
Probably not. Almost certainly not.
Well, how would I then travel across the universe if I wanted to do that? I think this is a leading question because I know, a famous colleague of yours back in the day asked a similar question.
Yeah. Well, it was a guy, a close friend, Carl Sagan, had written a novel called Contact. Well, he'd originally written a screenplay, and then he turned it into a novel when the screenplay wasn't getting made into a movie very fast.
Why would anyone make a movie like that? Right.
Anyway, so he wanted his heroine, who became Jodie Foster, to travel through a black hole to the vicinity of the star Vega. And so he sent me the page proofs of his book. Mm-hmm. He was already at the point nearly ready to publish. He waited a long time,
yeah, I know.
And said, I might be in trouble. Can you help me? And I read them driving up to driving up to see my daughter graduate from UC Santa Cruz.
Okay.
I read them in the car and fired off a response and said, well, you can't do it with black holes. She's going to die inside.
That's a short movie, yes.
And so you want to use a wormhole, and a hypothetical object that is somewhat similar to a black hole in the sense that it has a spherical mouth that is sort of like the horizon of a black hole, except you can travel two ways through this mouth. You can travel in and back out, and you go through it, and it leads to another place in the universe.
And just so we're not getting in trouble with the physics police here, black holes really exist. Wormholes not only are hypothetical, but what are the chances that wormholes exist in the real world?
I think the chances that they exist naturally are exceedingly small. The chances that they can be made by an very advanced civilization are bigger, but still small. And if they get made by an advanced civilization, they probably implode before you can travel through them. The chances that the civilization can stabilize them so you can travel through, again, are small, but not zero. And so the issue is that motivated by Carl Sagan's question and by my suggesting that he used wormholes in what became the movie Contact, I and other of my physicist colleagues started working hard to try to understand, do the laws of physics allow them? And it was obvious already from the beginning that they would, unless you did something very strange with them, they would self-destruct. They would implode. Quickly, yeah. And trying to sort that out. And to my surprise, we couldn't get it sorted out fully. But the work that has been done points rather strongly to a conclusion that probably they can't exist. And if they can exist, they very probably can't exist naturally.
Yeah, so this was circa late 80s, early 90s?
So the work on this continues to today, but at a small level. The bulk of the research on this was done late 80s, early to mid-90s. But it still continues because the answer isn't in.
Right, we still don't know. So Carl Sagan wants to let Ellie Arroway travel across the galaxy. You say it should be a wormhole, not a black hole. And then you realize, wormholes were, again, coined by John Wheeler. Is that true, the phrase?
So the phrase was coined by John Wheeler. The concept actually goes back to Hermann Weyl, about 1922.
I did not know that. Yeah, I would have given Einstein credit, but...
Yeah, so it was conceived perhaps independently by Einstein and his colleague Einstein and Rosen in 1936. But you go back and you find it in Hermann Weyl around 1922. But it was John Wheeler who really pushed hard to understand these initially because he had intuition, which may have been right, that on very small scales, what we call the Planck length, the scale where space and time as we know them must become probabilistic. They fluctuate like anything in the universe fluctuates due to quantum physics. On those very small scales, John Wheeler argued that you would likely find a froth of fluctuating wormholes.
Right.
And so that was his central focus.
There's this rough problem. Maybe this is getting a little bit too technical, but I can't resist. So Einstein gives us this equation for general relativity, Einstein's equation, and we might want to say, well, why can't you just solve the equation? And part of the problem is there's a left-hand side which says space-time is curved, and there's a right-hand side which says there's stuff in the universe, matter and energy and so forth, causing space-time to curve. And the left-hand side with the curvature is very pretty and understandable, and the right-hand side with stuff is kind of a mess. Is that about why we don't understand wormholes very well?
Well, that's maybe a piece of it. That's a piece of it because although wormholes are things that are made from warped space-time without matter, if you have them made from warped space-time without matter, then they self-destruct.
Right.
So you have to put some kind of matter in them to hold them open. And that's where it becomes tough.
It's where the rest of physics becomes, and that's all a messy, terrible thing.
But the other issue, and this was the issue for Wheeler, is that when you get down to these very tiny length scales associated with quantum effects, that there you don't even know the correct laws of physics at all well. And so then you have to start speculating. And that's where he gave, I think, some pretty plausible arguments that you would have this quantum foam of fluctuating wormholes. But there the problem is you don't understand the laws of physics. For a big wormhole, you don't understand the matter well enough to be sure that whether you can hold the wormhole open with it.
But if you have a big wormhole and you can use it to travel across the galaxy very quickly, don't you worry because special relativity says I can't go faster than the speed of light. It's like going backward in time.
Oh, come on.
I'm leading you down
sure
somewhere.
You can go faster than the speed of light. We all know. But not locally.
Right.
So let's be more precise.
Yeah.
Okay. So the universe is expanding, as we know. You're a cosmologist. You understand this far better than I do, Sean. And the most distant part of the universe is moving away from us faster than the speed of light. So we can't see it because light can't get to us from it, but it's doing it. And so what the speed limit really says is that if you have two objects that are close enough to each other that there's no significant warping of space and time between them, then they can't move faster than the speed of light with respect to each other. But when you've got a wormhole, you've got lots of warping of space and time, and all bets are off.
Right. So you can just... And ever since, I don't know if Contact was the first movie to use wormholes to get people across the... And now every movie does it. Yeah. So yeah, Star Trek has done it and everybody else. But then, I don't know whether it was you or your collaborators, but you began to realize that if you can travel across great distances of space, maybe you can also go backward in time.
Yeah. So that was me in this case. I mean, other people had... working in relativity had seen other ways that you might be able to go backward in time. This was just one more way,
right?
But one that became particularly popular, maybe because of Contact.
Well, no, to be more fair, I would say that it was, you could imagine building it. Like a lot of the other ways to build time machines started by saying, imagine you have an infinitely long cylinder, right? And at least the wormhole is contained in some region.
And once you have a wormhole.
Once you have a wormhole.
So with a couple of my students, Mike Morris and Ulvi Ertziever, I worked out how you would, if you had a wormhole, how you would use it to make a time machine. It's fairly simple. You just take one mouth, and I put my wife in one mouth. She carries that mouth out through the universe in her spaceship and comes back at high speed, and time for her slows down, as seen in the external universe. Right. I said on Earth it doesn't slow down. But as seen through the wormhole, our clocks run at the same rate. And so you begin with the clocks always run at the same rate, hers and mine, as seen through the wormhole. When she comes back, she's very young and I'm very old, as seen through the exterior, as seen through the interior of the wormhole. We're the same age. And so there's something crazy going on. The craziness is that you created a time machine.
Right.
So that was fairly simple and fairly obvious, but... I think, yes, you're right. This was something that if you had a wormhole, you could actually make it. And so then the question became, what do the laws of physics say about this? Could you really do it? And there comes in the key thing that things, if you're an engineer, in a very advanced civilization, and you can do anything that is allowed by the laws of physics, you've got to look at more than the laws of relativity. The laws of relativity say, yeah, sure, you can make a time machine.
Yeah.
But you've also got to look at the laws of quantum physics and the behavior of matter. There's always going to be some matter present because of quantum physics. There's always at least a little bit of fluctuating matter present. And so you then ask, okay, now you've got a wormhole, you turned it into a time machine, relativity allowed it. What did quantum physics do? What did it say? And the answer is that quantum physics says with high probability that the wormhole is going to self-destruct the moment you turn it into a time machine.
It seems like from various different perspectives, the universe is kind of reluctant to let you build a time machine.
It does seem that way, doesn't it?
Would it bother you if we could build a time machine? I mean, there are logical paradoxes involved, right? Can we
think
wriggle
it'd be
out of
wonderful. And anything that says that the laws of nature are different than you expect is wonderful. You're going to learn wonderful things.
Is that how you knew in the early 70s to think about gravitational waves? Because you visited back yourself in the past, gave you a hint? Well, So then you immediately do worry about paradoxes.
And so that's what I did with, again, with students and colleagues. And so we asked ourselves, okay, suppose you do have a wormhole, you did turn it into a time machine successfully, it didn't self-destruct in the process. Then how do you deal with these paradoxes? How does nature deal with these paradoxes? And so what we did was a dear colleague of mine and yours, Joe Polchinski, who just passed away, sadly, fairly recently,
right.
A really great theoretical physicist. He had been a student of mine years ago, decades ago. And Joe sent me an email. I think it was an email. Maybe it was a letter in those days. This is
the dawn of the early emailed age, yeah.
And he said, here's a little thought experiment. You send a billiard ball into a one wormhole mouth, and it comes back out of the other mouth before it went in, and it hits itself and prevents itself from going in. How do you solve that paradox? So we call this Polchinski's paradox. And so together with some students, I worked out what does nature say about Polchinski's paradox. We found that there are multiple ways that nature can get out of it.
Okay.
The billiard ball goes in. It gets hit a very gentle blow by itself on its way in. So it goes in, it comes out on a slightly different trajectory than it was supposed to, and hits itself a very gentle blow. So everything's all right. But there are a number of different ways it can do these gentle blows, and so you wind up with more than one solution to the laws of physics instead of just one solution. Where you thought there were none, you thought there's no way, no answer to what happens to the billiard ball when it goes in, because you've got a paradox. At first sight, you say the billiard ball goes in, it comes back out, it hits itself and prevents itself from going in. That's the trajectory. And then you find a trajectory where it's modified itself, and then you find another one, and then another one. And in the laws of classical physics, there had not ought to be multiple solutions. When you pose initial conditions, there should not be multiple answers. And so then you go to quantum physics, and you ask, what does quantum physics say? And so it becomes a very interesting game intellectually, trying to figure out how does nature get out of this. And it's much easier to deal with this with billiard balls than with human beings who go back in time and try to kill their grandparents.
That's the more common thing, but Joe is a good physicist, honed in on the simple physics problem. So it's interesting because on basic features of sort of logical consistency, we would not want to have a true paradox where two incompatible things happened. And you're saying that it seems that at least at the classical level, what nature gives up on is not logical consistency, but predictability. There's more than one possible way out.
But then we pay attention to the fact that the world is really fundamentally quantum at the bottom. And so where you have these multiple solutions classically, you go in and analyze them quantum mechanically. And what is you and I would call a WKB approximation. This is getting jargon.
We'll footnote that. Okay, there's a good approximation scheme we can use.
Anyway,
yeah.
and so you see that the quantum physics probably has a solution to get around this, and there's probably one unique solution. So my bottom line with this, and my problem is that I was just deep into this and felt like I was making some progress in understanding how you would deal with paradoxes, when LIGO got funded. And I said, do I spend my rest of my career now working hard on making gravitational waves a success, or do I think about time travel paradoxes?
I love time travel, but you made the right choice. Yeah. But when you mentioned quantum mechanics there, just because I know probably some people know a little bit about the idea of branching the universe off because you have a time machine and creating a new timeline. And that's not what you're talking about, is that right?
No, it's not at all what you're talking about.
You're just using quantum mechanics to find the one consistent, most probable trajectory of what actually happens.
And so what you really want to do is ask, how do you formulate quantum mechanics in the presence of a time machine?
Right.
And in fact, there is a way to do it, and it's using a formulation of quantum mechanics due to our dear friend Richard Feynman.
Yeah.
And but a generalization of Feynman's ideas due to his colleague Murray Gell-Mann and Jim Hartle. And so the tools are there.
Very Caltech-y feel about it.
Very Caltech-y field. That's right. Well, with Hartle, it's Caltech in Santa Barbara, but. The tools are there to do this.
But wasn't Jim a grad student at Caltech back in the day?
He was Murray Gell-Mann's grad student.
Yeah, all right. So
and John Wheeler's undergraduate and postdoc. Okay. But anyway, you can formulate quantum mechanics in a way that handles all this in the presence of what we call a closed timeline, in the presence of a time machine. But for me, the beautiful thing about this is that once you've done that, you discover that information gets lost.
Right. Physicists don't like this.
And physicists don't like
Some physicists
that.
Some
physicists don't like this, but I think it's quite wonderful that, anyway, and so then you get caught up in the so-called information loss paradox, and a view of this that I have that's iconoclastic, that differs from that of the majority of physicists.
But it's a good little lesson about how, you're fooling around in some sense, right? Like you weren't trying to build a time machine. You were inspired by a question from Carl Sagan, but it leads you to some maybe interesting insights into questions people really care about.
Precisely. And so I came to appreciate that in areas where you're dealing with physics beyond where we can actually do experiments today, someday we will, but not today, thought experiments like these, simple thought experiments, like what happens to billiard balls if they collide through a wormhole that has a time machine built into it. Simple thought experiments can sometimes dig pretty deeply into the laws of nature